Hi everyone. I hope you had a good lunch, and I'm very glad you joined us this afternoon for this training. My name is Michal Kurka. I am a software engineer at H2O AI, and I work on the open source product H2O 3. And I would like to use the next 50 minutes to give you an introduction to H2O 3. But before we do that, I know you had the driverless AI session in the morning, so most of you probably already have the aquarium setup done. But for those of you who came just for the afternoon sessions, I will just remind you how to set up aquarium. And you will need to go to aquarium.h2o.ai and after you register and everything, then please click on the dashboard, and in Browse Labs you should see Introduction to H2O and Sparkling Water, which is the lab that we will be using. And after you click on the detail, you will be able to start the lab. I already did that myself. We have two versions of the lab prepared. We have one for R users, and it will be done in RStudio. And we have second one in Jupyter for Python users. For the demonstration purposes on stage, I will be using Python. So if you are kind of not sure or you don't have a preference, I would recommend to use the Python one, which is what we will be doing up here. And otherwise, you are free to use the R one. It should be very same to the Python one. So you will not lose anything by doing that the R way. But let's go back to the presentation. Also, I will do this very quickly. I will not spend too much time in aquarium because most of you already have it. And if you have any questions, there are tutors around you. Anybody in the same t-shirt as I have, ask them questions and they will be able to help you. Okay, so what will be our agenda, what we will be doing the next 50 minutes? First, we will spend a little bit of time, not too much, on what is machine learning, and then we will go into how you can apply machine learning, or how can you apply machine learning with H2O open source. This will be very quick, and then we will spend the rest of the time on actual use case. The labs is all centered around the Amazon reviews data set, and we will try to do some feature engineering with H2O. We will do some supervised learning, build some models, and evaluate the models with H2O. Then I will hand it over to Erin, our chief machine learning scientist, and she will talk about AutoML. And at the end, we will have Q&A session if the time permits. Okay, so I met some of you at the H2O open source booth, and I know not everybody is a data scientist, so that's why I have this slide that talks about what is machine learning. If you Google machine learning definition, you will get many convoluted definitions, and you will not make any sense out of it, but this one is a nice one. It's a very simple definition that says machine learning is the science of getting computers to act without being explicitly programmed. That's a beautiful definition. And just like in machine learning, simple models are sometimes better than the complicated ones. I think this simple definition is better than the convoluted one that you can find on Wikipedia, for example. But what this says is that when you are doing machine learning, and it's not just science, it's maybe a little bit of art as well, you don't actually need to provide any domain expertise to the algorithms. The algorithms are generic algorithms, and they learn from the data you provide to the algorithms, and they interfere. They are able to learn the patterns from the data. What kind of use cases can you solve with machine learning? You can, for example, try to predict if a customer will default on a credit card payment based on his past behavior. You can look at the attributes of the customers and find customers that are somehow similar and have different segments of customers, and maybe you want to treat the customers differently, you want to do some target marketing, you want to just understand the data more. Or what we will do today, we will try to predict customer sentiment, how the customer feels about a product based on a text review of the product. So machine learning is all about finding patterns in the data. If you saw this picture and I asked you and pointed at a blank spot in the picture, you would probably be able to say whether the new observation there should be red or it should be green. It should be a square or it should be a circle. And that's what the machine learning algorithms are trying to do. And they are trying to do it in a way that's not perfect. They are trying to not to overfit on the data, memorize the data set. So this green dot in the sea of the red squares, would you say if everything was normal, would it be green or red? I would probably say that's an outlier. It should be classified as red normally. So the machine learning is done in a way that the model should be something that generalizes. It should not just memorize the data you provided, but it should be able to do more. When you give it new data, it should make reasonably good predictions on the new data. Machine learning can be divided into branches. Supervised learning and unsupervised learning. In supervised learning, we already know the outcome. We know what we are trying to predict. For example, how much will a customer spend in his next transaction? We know what to expect. And we know what we want to learn. What function are we trying to learn with the machine learning algorithm? And that's the question of how much a customer will spend. It's a regression problem. We are trying to predict a numerical response. Other type is classification. We have two or many classes, but finite amount known classes that we are trying to classify into. And for the simple case of binomial classification, we can just say yes or no, will the customer churn or not, and H2O has you covered. We have we have implemented algorithms for both of these problems, and we will talk about some of them later during the hands-on. The second branch of machine learning is unsupervised learning. We don't have any clear outcome that we want to predict. We just want to learn something about the data. And we can, for example, learn what clusters exist in the data, if there are any groups that behave similarly, and again, as I said, we have the algorithms to do that. Other way is feature extraction. You have data set. Maybe it's a very wide data set, and you don't want to use the wide data set for the GBM or some machine learning algorithm that's after that. You might want to compress the data set to just certain features, so you can use our principal components analysis. Or you have a text data set, and text data set is not naturally understood by the machine learning algorithms like GBM or GLM. So you might want to preprocess the data, and you might want to use our implementation of the word-to-vec algorithm that takes the text and maps the text to numerical representation. It will be vectors of high-dimensional vectors. And this is what we will do today, and I hope you will like that. It's a nice use case, and word-to-vec is a very interesting algorithm. The third thing that's mentioned on these slides is anomaly detection. You want to find outliers or some anomalies in your data, something that does not follow any rules that seem to be in the data. So you might want to use it if you want to mark a transaction that was made on a credit card as fraudulent or not. And we again have algorithms implemented for these use cases. Okay, so now that we set the base, some understanding what machine learning is, let's talk about how H2O specifically, H2O open source can help you with solving the machine learning problems. H2O, what is H2O? H2O open source is an in-memory machine learning framework. What we give you is a set of tools that you can use to solve your real-world problems. We have implemented many of the most popular and widely used machine learning algorithms, like generalized linear models. We have random forest, gradient boosted machines, deep learning, and we have much more, and we are adding more with every H2O release that's coming every quarter, basically. H2O should be easy to adopt. If you are familiar with Python or R, you can install our R package or Python package and start calling the H2O functions, and they should not really be, they should really be familiar to you. We are trying to adopt APIs that may make some existing APIs. It should not be something completely new. If you are not a developer or engineer, or if you don't data scientist, if you just don't know how to code at all, that's fine as well. We have also our web UI, we call it Flow, and Flow is a point-and-click interface where you can build a machine, load the data set into H2O, build a model, inspect the model performance, and learn something about the model. And some companies or some users just will use the Flow UI. It is very powerful. But we have integrations for other software pieces because it's everything built on Java and exposed REST API, so you can call it for almost anything. Okay, but how is it different from the other frameworks out there? There is R, there is XGBoost, there is scikit-learn. Why would anybody use H2O? So where's the value proposition? And I think the biggest value that we have is that we don't limit the amount of data you can process. You can start H2O on a single node, on a laptop just like mine, or you can go to AWS and start a 100-node cluster and process terabytes of data. H2O is implemented in a way that everything is parallelized, everything is distributed, it's very scalable. And that's our main value, what we are bringing to the table. We believe if you let it work with the whole data set, no sampling whatsoever, then you can get to better models. And that's where we should excel. The big data is our strong suit. Of course, building the model is not the only thing. It's not where it ends, but you will also want to deploy it to your production environment, and you want to integrate the framework into your existing environment for the model training. And we are integrating with the most common frameworks that are out there. We have integration with Hadoop. We run on top of Spark. In our sparkling water product, you will hear it in the next session. We are able to ingest the data from different kinds of data sources, ranging from HDFS, Amazon S3, local file system, network file system. You can read it from relational database. And we can add more. If you ask for it and enough people ask for the same feature, we will add that because we want to make our users happy and do what the people do, actually. Okay, so once you load the data from any of these data sources, you can do some exploratory descriptive analysis, learn about the data set, do some feature engineering, feature selection, and build your model, evaluate the model. And once you do this several times and you are finally happy with the model, you will probably want to keep it in something that we call a model deployment package. It's our Mojo. Previously, we had the Pojo, and that was just Java class, but now we are more focused on the Mojo, and that's the primary way how to put your H2O model to your production scoring environment. And Mojo has a Java runtime, which means it can integrate with almost any Java environment you might have. If you have Oracle database, Oracle has a ability to run Java user-defined functions, you can use Mojo in Oracle database. But if you don't, if your environment is not necessarily Java-based, you can still expose the predictive capabilities as a microservice, and we have templates or, let's say, set of guidelines how best to integrate H2O in your specific environment. And the natural ones are Spark, Kafka, Storm, Hive, but it's virtually limitless. You can do almost anything. Okay, let's go to our use case that we will be working with today in the hands-on part of the session. And we will be using the Amazon 5 food reviews dataset. The original dataset has over 500 food reviews. We will be using just a subset of that so that everything is fast for the demo purposes. But the individual rows look something like that. It's not that much information, just a few columns. It has information about the product, product ID, user ID, but we don't know what product. We just know some product. We don't know anything about the user. We have only the user ID. What we do know is how many people found the review helpful, how many people gave a thumbs up. I want to remind you it's Amazon, so you can click if the review is useful or not. And that's the helpfulness numerator. The helpfulness numerator is how many people rated the review, either gave thumbs up or thumbs down. Then we have the score. That's the star rating the customer or user gave to the product. And we have a timestamp when the review was written. We have a short summary, and we have the full text of the review. And for our use case, we will try to predict whether a user liked the product based on the text review he has written. And we will make our lives a little bit more simpler. We will not try to predict exactly the star review, but we will just try to predict if the sentiment of the user is generally positive or not positive. And positive we consider 4 stars or 5 stars, and everything else is not positive. I have links to the notebooks I will be using, so if you, for whatever reason, don't want to follow this tutorial now, you can do it at your convenience at home. Everything will be published online. It's in our GitHub repository. Documentation to the word-to-vec algorithm that will be essential to generate good features in our modeling is also provided and linked here. So if you want to take just one picture of the slides, this would be the one to take. Okay. I don't think I need to show the workflow now. I will just switch to the lab, and I hope everybody has it running by now. And I will use the one that's in Jupyter. The password is H2O. And please follow me. I will be trying to go slow. And click on the H2O3 hands-on. And pick NLP. We'll be doing natural language processing today. And for Python, click on the Word Embeddings IPython notebook. If you don't want to run anything, click on the pre-run version, and that also has not just the cells, but it also has the output. And I'm sure our users will figure out how to get to the right demo. It's the same thing, H2O3 hands-on /NLP/wordembeddings.r. So let me make it large, and I hope you can now see that. Okay. So it has this tutorial has 10 steps. I don't know if we will do all the steps. I don't think we will do the AutoML step. That will be Erin, LeDell, who is an expert in AutoML. So we will probably stop around step 7. And this environment has all the packages pre-installed, and one of the packages that you need to with H2O is the H2O package. If you want to install it from, let's say, pip, you just go like pip install H2O, and you will get everything you need. H2O is not a native Python package. The backend is implemented in Java. As I mentioned, H2O is scalable, distributed. It's not limited to your laptop, and you can have a small single node cluster, or you can have a hundreds of nodes cluster. So what we are seeing here is just the Python client. Where the work will actually be done is the backend, and the backend is in Java. written to optimize for speed. We are trying to make the experience good by optimizing for the best possible speed. So if you want to use H2O, I didn't import the package. So import the package first. And what's happening now that H2O is starting the Java backend. You can also start it outside of the Python notebook and just connect to it. But if you are just running on a laptop, it might be easier to start it from Python as well, using the H2O init function. And now we see that H2O was successfully started. It's reporting its status, and you can see that it has about 7 gigabytes of memory, which is more than enough for the purposes of the demo. Once H2O is running, you can start importing the data. H2O can ingest data from different file formats. Obviously, CSV is one of them, and the Amazon find food reviews are stored in CSV. So we can just run that. It should be very fast. It's not a big data set, which should we see right away. We downsampled it just to 100,000 rows, and there's only 10 columns. So let's start exploring it more. You can see the actual rows, and they will be similar to what I showed you on the slides. You can see that the product ID, the short summary, the score rating, the other information, and also the text of the review. And some of the reviews are actually very interesting. But we will not go into that, and we will check the distribution of the scores that the users gave to the products. And you can see that 5 stars is by far, the most popular, most frequent score. It makes some sense. When I'm shopping on Amazon, I filter just to products that have, let's say, 4 stars or more, and the bad products don't get to be bought, and they don't get the reviews. So this data set is very imbalanced, or it is imbalanced. The negative reviews are definitely a minority. Let's look at the most frequent summaries. What do people say? So it is a fine food reviews data set, and it's a good thing that most people are satisfied with their purchases and find the product delicious and yummy. But we will also see the bad side of this data set later. As I mentioned before, we will not try to predict exactly the star review. We'll make our lives easier by predicting whether just it's a positive review, the user generally liked the product, or if it is not positive, neutral, or negative. So I will do that. And while I'm doing that, I will tell you that so far it was probably not that much different from what you are doing in your daily lives as a Python data scientist. But what makes it different that this is actually executed in H2O. The reviews, it's not a pandas frame, it's an H2O frame that doesn't exist on the Python client. It's just a reference to the Java backend, and all the work, all the data crunching, and obviously machine learning is done on the backend. But from your point of view as users, you should not see the difference. So yeah, and let's see how the distribution looks like now. So we see that we have about 78,000 positive reviews and 20,000 reviews that are not positive or negative. And at this point, I would like you to introduce to a word-to-vec algorithm that we will be using. When you looked at the rows of the data set, there is really not that much information, is it? We have the product ID, we have the user ID, but they look meaningless, at least to me. And we have the summary, we have text. Traditional or classic machine learning algorithms don't deal with text. You cannot just take this and feed it to GLM or GBM and expect to get great results. Or maybe we will get great results, and we will try that. But I would not expect that. GLM and GBM will by default drop the text columns. They will not do anything to it. And because we believe the data in the text column will be probably important, we will need to learn about a new algorithm that can work with text data. And in H2O, we implemented word-to-vec algorithm. Word-to-vec algorithm is an algorithm that takes text corpus, usually giant text corpus, think like really Google scale or the Google News or all the works by Shakespeare or whatever, something really significant amount of data. And based on this text corpus, it learns word embeddings. I will take any word like yummy. Yummy is a word that's present in the data set. And the word-to-vec algorithm will tell me that for yummy, the word yummy, I can represent with a, let's say 100 numerical values. I will create an embedding in n-dimensional numerical space. Typically, it's hundreds of dimensions. And this kind of embedding, this kind of mapping will somehow capture the meaning, the essence of the word. And word-to-vec algorithm is great in that you can use it to find analogies. You can find synonyms. You can solve problems like king is to queen, like man is to what? Question mark. And with word-to-vec algorithm, you can find out that the question mark, the solution to the problem is woman. Or you can find syntactic relationships between words. It is a very powerful algorithm, and it's a good algorithm to play with. And we will see that hopefully when we are trying to find the synonyms of the words that are in this data set. To use word-to-vec in H2O, you will need to preprocess the data a little bit. You will need to do some data cleaning. First thing, what we will do is to remove stop words. Stop words are words that don't add really any meaning to the sentence, to the message, like indefinite article, definite article, or very frequent words like do or don't are stop words. So this function will do the preprocessing, this tokenize function will do the preprocessing, and I will run it all because it takes a little bit of time to tokenize the whole data set, and in the meantime I will be talking about what it is doing. First, it breaks the reviews into sequences of words, and it converts everything to lowercase. We don't need to worry what's uppercase, lowercase, just convert it to all lowercase. Then we will throw out some data that are probably not needed, which in our case are words that have just single letter or have or have numbers in it, and then we will filter out the stop words, and we will get the data set that has just a single column that can be used as an input to the word-to-vec algorithm. We still preserved the reviews. We have separators in the data. In this case, you cannot see that, but the reviews are still preserved by a special separator, so we know what words belong together. Once we have the word-to-vec algorithm, we have the input for the word-to-vec algorithm, we can actually start training it. And we can do just the default parameters, the default options, but I wanted to visualize the word-to-vec. It's easy to visualize that and also give you some results really fast. So I'm limiting the vector size to just 2. As I mentioned, usually it is hundreds of numbers for the vector, hundreds of dimensions, and 100 is probably the most common. But for the purposes of the visualization, we will just use 2. And this is not what you would actually do when you are training a model that you want to use later. This is just to play with for now. Let's start looking at and it finished. The training already finished, and we can start looking what it did. So as I mentioned, it takes the text corpus, it finds the dictionary that's used in the text corpus, and it creates the mapping. So in this case, it maps the word made to some two-dimensional vector, and you have no way of telling what it is. It's something. The algorithm figured out this is a good embedding for this data set, and this is the vector that somehow captures the semantic meaning of the word. What we did in the cell 16, we used H2O transform function that takes the model, the sample embeddings that we trained just before. It doesn't aggregate it in any way. It simply projects it to the two-dimensional space. And then we used H2O function cbind to take the source corpus, text corpus, and bind it to the embeddings. Make one frame out of it. If you want to extract the embeddings that the model learned, that can be done with H2O function toFrame, that just output literally what's stored in H2O. The output of the algorithm is a mapping, and you can get the mapping you can convert the mapping to your H2O frame and then to pandas if you want to, and play with it as you wish. We have many words to play with, and I cannot visualize all of them, so we selected just a bunch of few that might be interesting to inspect. So these are the selected words that we will be using, and I will use this to prepare the plot, two-dimensional plot of the embeddings. And sometimes it doesn't plot it right away, so I run it twice. If it happens to you, just run it twice and it should show something. And I must say that not all of you will see the exact same picture. The word-to-vec algorithm is by nature or by our implementation not reproducible. The embeddings might look like every time slightly different, but they should capture the same essence of the words. And what you see here is it's a very nice picture. I'm glad it turned out this way because it shows kind of three clusters of the words. And it has some chemical compounds. Probably this is a folic acid. Somebody was mentioning it in the upper right corner. In the center, close to the center, we have words that express good sentiment. I don't know if you can read it as I can, but it says sweet, savory, espresso, Starbucks, amazing. And the other one I cannot even read. But it's a positive sentiment, something that's probably associated with a good experience of the user. The third cluster, the one that's in the left corner, is on the opposite thing. It's a negative sentiment. It says support, unhappy, moldy, weighted, abdominal, expired, and email. So probably when the user was not happy, he called support, he emailed somebody, and that's why we see these words close together in the embedding space. And why am I saying all these things? This should tell us something. And what it does tell me, that there is a good chance that using the embeddings, I will be actually able to solve my task of separating the positive reviews from the negative reviews. Because by nature of the data set and how I trained it, it already looks like the positive words and the good experience words are organizing itself next to each other, and the negative sentiment is also organized close together. So this was just a toy example, two-dimensional word-to-vec embedding, but in real life, you will use vectors of hundreds dimensions. So that's what we will do now. And this will be probably the most time-consuming thing in this hands-on session, because we are working with a reasonable sized data set, and the word embeddings are by itself large or reasonably sized. Once we do that, we will have some fun with the data, and we will be trying to find synonyms to the word coffee or stale, but you can try any word that you might want to test and input it there, and it should find reasonably good synonyms as long as they come from the food something that might be in a food review. It will probably not be able to generalize to, let's say, Google News or something like that, but this data set is about food reviews. And this is all happening in the backend. It should be done soon. The algo is doing a bunch of iterations of the word-to-vec model and trying to learn the best embeddings for this kind of data. Once we do that, we will kind of do the same thing that we did before manually, how we inspected the clusters. We will do the same thing with a k-means clustering algorithm and see if we get similar clusters to what we already got. Okay, so it seems like it finished. And let's hope it will give good results. It seems like that was the case. To coffee, it's found another similar coffee, misspelled coffee, coffees, espresso, espresso brew. It's all somehow coffee related. To stale, it found moldy, rancid, inedible, expiration, and expired. So everything related to something that's not good. So this is a basic sanity check that you might want to do when you train your word-to-vec model and you use your experience with the data set. What kind of you have some expectations what you will probably get after running the word-to-vec algorithm, and this is what I always do to check if the results make any sense. In this case, it does make some sense, so let's proceed further. And this is the embeddings that the algorithm prepared on the data set, and I'm running the k-means model. The k-means is an unsupervised machine learning algorithm that's supposed to find clusters of the data. And in this case, I'm not specifying any particular number of clusters. I just want k-means in H2O to figure out the optimal number of clusters on its own, and it found 2 clusters. If I want to predict with k-means, I call on the model function predict, and I bind it again together with the words. So I see that the words have assigned cluster, and I can start looking what happened to my selected words that I had picked out before. And it seems like in one cluster, I have the good stuff. I have stuff like savory, espresso, yummy, salty, amazing, tasty, sweet. And in the other cluster, it must be logically the bad sentiment, moldy, unhappy, weighted, expired, support, and so on. So right now we are done with training the word-to-vec model. But let's forget about the word-to-vec model for a little bit and see if I can get a reasonable performance with just the original data without the text column. Let's ignore that I have any text in the data set, that I don't have the word-to-vec model. Let's just not use it. Let's be optimistic. Maybe I can solve this problem just by using the other columns, which are product ID, user ID, helpfulness numerator, helpfulness numerator, thumbs up, thumbs down, and the timestamp. I want to create a validation set, and I want to create it I want to have a time split, so I'm splitting this data set 80-20% based on time. So I have the training set, I have my validation set, and I will use the probably most popular algorithm for transactional data, and that's GBM. In H2O, we have our own implementation. You might be familiar with XGBoost implementation, which we also integrate. For the purposes of the demo, I will use our implementation. I will use the positive review as my target, as the response I want to predict. And you can see that I'm using AUC as the stopping metric. If you don't know what it is, that doesn't matter. I will also show confusion matrix, and it will give those of you who don't have understanding of the machine learning terms probably some more insight. And I will rely on early stopping. I don't want to overfit on the data set. I don't want to do what I showed with the picture with the red and green dots. I don't want to memorize the data set. I want to make sure when I train it, I will be able to generalize. So that's why I have validation set, that's why I have array stopping enabled, and let's start training the model. It's just few columns and 100,000 rows, so that's nothing for H2O, and I already have the results, and I see that AUC is 0.6, which is not great. And if I look at the confusion matrix, I see that I'm making overall 22% error, but if I remind myself how was the original distribution, I realize this is actually a model that's close to useless. I know that 80% of the data is positive reviews, 20% is not positive. And what the model did in this case is just predicting almost always that everything is positive. And it's not making almost any error when predicting the positive ones, but the negative ones have 91% error rate, and that's probably not something you would use for anything. So this is not a good model. And thankfully, I am prepared to make this model better. I trained my embeddings, and I can find out later if these embeddings are any good. But before we do that, I wanted to show you how you can inspect the model in H2O, see what variables or features are important to the model. And in this case, it's the thumbs up, thumbs down. And if I want to see what's the specific effect of the variable, I can see partial dependence plot that will show me with rising number of the thumbs ups, how the model was responding to it, how the probability was affected, and we can see that the more people gave thumbs up, the more likely it is a positive review. I guess maybe people give thumbs up mostly positive reviews, and the negative ones, they don't like as much. But again, we should not do much reasoning on this model because it's not a good model. So if I want to have a better model, I have my word embeddings. But the word embeddings, as we mentioned, they are trained per word. So for the word yummy, I have a sequence of numbers. I don't have anything for the review. So how do I get something that would represent the review? One of the simplest methods is just simple average the words that are in the review, and that will give me the representation of the numerical representation of the review that I can use. So I will use that because it's surprisingly powerful method, especially for this use case. And I got my vectors that represent the reviews. It's now all numerical and nice for the machine learning point of view. And I will bind them to my original data set. And again, I will do the split into training and validation. And I will train the same type of algorithm. I will train gradient boosting estimator or gradient boosting machines. I will cheat a little bit, and I will add a little bit more trees. Originally, I was just using the default, which is 50, but I added so much more information, so I want to give the algorithm a chance to actually leverage the information, and I will still do early stopping on AUC and see what the algorithm will determine is the optimal number of iteration, optimal number of trees. So let's do that. If you want to, you can see what is going on in H2O flow, which is the web interface I was talking about. I can just go to model, list the model. I see that I have two. This one is the one that we are just building right now. Oops. Oh, okay, it's still training, but it finished. And we see that it stopped earlier than after 1,000 trees. It stopped after 240 trees, but your results might be different because you might have different word embeddings. And now let's see if I actually got a better model or if I failed spectacularly. I just embarrassed myself on the stage. And that's not the case, fortunately. My AUC is now something like 0.9, and if I look at the confusion matrix, I will see that my overall error rate is 14%. I am still quite good at predicting the positive reviews, but I am much better at identifying which reviews are negative or neutral. Before, the error rate was 91%. Now I brought it down to just 43%. And let's see if the word-to-vec features actually play an important role in the model. And I can see that they do, and that makes sense because it's a better model. So actually the most important feature right now is one of the word-to-vec features, and we have no way of telling what this feature actually means. To us it's meaningless. We can try to find out a little bit more, but we will not do that in this talk. And helpfulness, the numerator and numerator are still playing an important role. So I got to a reasonable model just to relatively simple feature engineering in H2O. If I wanted to do better, I probably could, but that's out of scope of this hands-on. What I also wanted to show you that you can use the information that you got from training one model in H2O and leverage it to build another model. Yes, we built maybe a reasonable model that has 240 trees, but what if my production deployment requires that I score each new observation super fast? What if I have only nanoseconds to be able to score on the new observation? Then maybe 240 trees is good enough. Maybe I have super fast computer, maybe it's not good enough. And I would like to simplify the model. Find a similarly performing model that's much more simpler. And with word embeddings, that's a good use case to also try GLM. And yes, you can see we have the most important variables in the model. And I will just take the top word-to-vec features. This is what this cell does. It extracts the, oh, I see I have a mistake there. In Python, we start indexing from 0. So let's not make the model worse than it needs to be and take all the 10 most important features and see if I can use it as interaction terms in H2O. So when you specify interaction terms in GLM, it will try all the pairwise combinations of these features and include them in the model. And I will obviously use the helpfulness numerator and all the word-to-vec features as well. And I will train another model and see if this model is any good or if I really need to stick with GBM if I want the best possible accuracy. And it finished training, and it seems like it's doing similar as the GBM. So using something that I learned from the GBM model, I was able to extract this information, give the GLM model the interaction terms that are probably important because they were on top of the GBM model, and create a much simpler model. GLM is just a set of coefficients, so I will be able to score such observation super fast, and I don't have to worry about all these trees, and it probably simplifies my deployment as well. So I have another much simpler model that I can consider. What I want to say that the AUC we see here, we should probably not use to judge whether the GBM model is better than the GLM model. We should use an independent data set that to test this, to see how the performance is on the test data set, and because we don't want to overfit on the validation set, we use the validation set for error stopping. So in real life, you would probably have a third portion that you would use to evaluate how good the model actually is. And I can still look at the confusion matrix of the GLM embeddings, and it's basically the same as for the GBM embeddings. So it's a very similar model, but much easier to score and more understandable. Of course, the word-to-vec features you cannot understand, but in general, GLM is naturally interpretable. Okay, I think I am out of time, and I also finished what I wanted to talk about. At this point, I would like to invite on stage my colleague, Erin LeDell. Erin is our chief machine learning scientist, and she's an expert on AutoML, and she will tell you how to do all this, almost all this, in an automated way. Okay. Oh, you don't.
I have.
Yes. Sorry. Okay. You have everything different, I see.
It's okay.
Okay, you're good.
Okay, so I think my mic is working. So thank you, Michal, for taking us through the first part of our H2O3 training. So the last part you'll see on the script, if you still have it up, there's a little step that will have you run AutoML, but what we're going to do is actually move to another script, and so that one will focus a little bit more just on AutoML, and we'll use a different data set. So I will show you where to do that. So if you're still in aquariums, you're going to look in the H2O. If you're in Jupyter or if you're a Python person, look in the H2O3 hands-on folder, and there's a folder called AutoML. And there's one file in there called Lending Club AutoML. And if you're a Python user, that's your file right there and what you're going to use. And then if you're an R person, the R script didn't get copied into the AMI, so we're going to copy paste it in there. And if you click on this link here, that will bring up where the code is on GitHub. So I will give you, I'm just curious, how many people are R people? Okay, you can be both R and Python if you want. How about Python? Okay, so, all right. I'm just going to leave that survey anonymous for now. But yeah, we have a lot of data scientists in the room. How about, how many of you are more interested in using the Flow GUI interface? Okay, so cool. All right, so if you are Python, try to bring up that Jupyter notebook, and if you're in R, we're going to click on this link, and what it's going to do is bring us to the file. And if you go back to your aquarium and you clicked on the RStudio, you're going to bring that up, and you're just going to copy paste that. So if you go click on raw, we're going to copy, and we're going to paste just right into, if you don't have a file open, you just go to File, New File, RScript, and then you're just going to paste it in there, and then you will have the code as well. So I'll just give you another second to do that. Okay, so what we're going to do actually is we're going to skip right to the code, and then we're going to have AutoML run for about 6 minutes. And so while it's running, I'm going to skip back over to my slides, and I'm going to explain a little bit more about what AutoML is doing. So let's just jump right into the code. I'm going to use the Python notebook. All right, so let's actually what I'm going to do is I'm going to shut down the cluster and then start it back up. Okay, so Let me make this big. Okay, and the reason I did that is just because I already ran it once and I want a clean cluster. So this you've seen before, import H2O, H2O.init. You don't have to pass in an argument here, but if you want to have more memory for your H2O cluster, you're going to have to tell it some number there. So 6 gigs, or if you have a big cluster, 60 gigs, et cetera. Yes? Yeah, I can post the R link one more time. Let me just go back. So I'll leave that up for another minute if you didn't get it the first time. So tinyurl.com/aml-rcode. Okay. All right, is there anyone else that needs that? Okay. Oops. Okay, so let's go back to the notebook. All right, so we started up our H2O cluster. So this is running in Aquarium if you're doing it this way. We are going to import a data set. So this is a lending club. So that's basically a loan company. And the goal with this data set is essentially to figure out whether or not somebody's going to default on their loan. And from that, then you would assign them an appropriate interest rate. So that's kind of the idea here. So we're going to load this data set. And so if you're running this on Aquarium, this file is already on the image, so it's just a local file. And if you for some reason are running this on your laptop, the URL for the file is here. I think there's actually a typo in it. I think there's an extra data. So if you need that, I would copy it from the R one. It's there, make this big. And while I have this up, we're just going to look at some of the columns. So loan amount, the length of the term of the loan, employment length. So these are all things that you might think are correlated with whether or not somebody would default on their loan. And the actual column name is called bad loan, which is what we're trying to predict. All right, so let's import that data set. And the first thing that we do, and I don't remember if Michal talked about this or not, but when we are trying to do a classification problem, so this is a binary classification problem, they either defaulted or they did not. So the way that H2O knows whether or not you want to do regression or classification is how you have encoded the response column. So if it's a factor or categorical type, then H2O knows it's going to be classification. If it's just numbers, numeric type, then it's going to try to do a regression. And so sometimes it's a little ambiguous. So in the case where you would have like a true or a false or a yes or a no, it's obvious when you import the data that that's a categorical type because it's words. So, but sometimes if you have zeros and ones, it's ambiguous whether or not is that supposed to be a regression or a classification. So when it's a 0 and 1, which is how it's encoded here, we want to make sure to explicitly convert the type to factor. So this is just an H2O thing, and this is just something that you just have to remember to do. And if you forget and you get a regression model back instead of a classification model, then you'll know that you forgot to do that. So this is if we just look at the data again. So this is 163,000 rows. So how many of you use data bigger than this on a regular basis? Okay. How many of you smaller? I guess people are more shy about using small data. So there were a lot of hands that went up. So this is just like a demo, but for a typical machine learning problem, maybe this is pretty normal, 163,000 rows. If you're using another library that's not so scalable, that might be a lot of data, and it might take a long time to train. So what I'm going to show you next is just H2O AutoML function has the same interface as all the H2O functions. So you need to specify a few things. One, the training frame argument, so that's just the training data. And then we have an X and a Y. And X is just a list of the predictor columns, and Y is the response column, or the thing that you're trying to predict. So if your response column if your predictors are everything except for your response, you don't have to actually specify X. But in this case, we're just going to be explicit. So Y, we said, is called bad loan. And X, we're going to take all the columns, but then we're going to remove the response, and then we're also going to remove the interest rate. So this is just has to do with the data leakage. How many of you have heard that term, data leakage, before? So that's when you have a data set that has some column in it that really shouldn't be there because it's kind of like hiding the answer in the column. So that the interest rate, which is actually kind of what we're trying to assign, is actually in the data already, so we're going to remove that. So that's what's going on there. And then here's the basic interface. Let me just make it a little bit bigger. You have to set up AutoML. So there's a couple ways to tell AutoML how long to run. So it's either the number of models that you want it to train or the length of time. So I typically tend to use the number of models because it's reproducible. So if you run it another time, you get, if you say 6 models, you're going to get 6 models the second time. If you say run for 10 minutes, it might be able to do more in the first time you run it than the second time, depending on what else is running on your machine at the time, if the resources are different. So, so it's up to you, whichever one you like to use. You can use either or both at the same time. And then there's other arguments. I won't go into all the details of all the arguments, but one that we just have here, and this is doesn't actually do anything because we're running it for such a short amount of time, but you can exclude types of algorithms from AutoML. So the list of algorithms that it runs is like random forest, a random forest with extremely randomized trees, which we call extremely randomized random forest. It's just some more random forest. Anyway, then GBMs, so H2O GBM, then we have XGBoost in there now. That's actually a new addition to AutoML. We have deep learning. We have GLMs. So basically all the supervised machine learning algorithms that we have in H2O we'll put in AutoML. And okay, so let's get this running because it'll take 6 minutes to run this on this machine. So I think you all have basically the same resources available, so it should take everybody the same amount. So let's just run this. Okay, and so there's a little progress bar, and it's going to go do its thing. So we started, okay, so I'm just looking at the time so that we will come back in 6 minutes and check on it. Okay, so now while that's running, let's go talk about what it's actually doing. Okay, so this is just kind of an overview of things that we can automate in machine learning. So essentially, as a data scientist, your job is to prepare the data so that you can do modeling. So that might include all sorts of things, which I'll go into more detail on the next slide. And then you typically can't predict what the best model would be in advance. And possibly that's where AutoML is going, like a few years from now, where you wouldn't have to run all these models. You could just predict if we gather enough data. Eventually that might happen. But for now, we have to generate a bunch of models and then either find the best one, or we can optionally create an ensemble of either some of the models that we created or all of the models. So the term AutoML is pretty generic, and it's a lot of people use it to mean different things. So I wrote this blog post a few months ago, and the URL, if you want to click on it, it's on our blog, but it's probably easier just to go to tinyurl.com/flavors-of-AutoML. So this is just a blog post that explains all the different uses of the term. So I think we were the first people to name a tool AutoML, H2O AutoML. Google also has something that they call AutoML now, and it's very different, and it works basically on image data or text data. So if that's not the type of data you have, then that's not a tool that you can use. So essentially the blog post just goes into like, how do you pick a tool and what are the different types of AutoML? And it basically just, it's determined by what your data looks like. So if you have a certain type of data, you're gonna use a certain type of tool. But the goal is the same, just to automate the machine learning process. So if you're interested to learn more, you should read that post. Okay, so here's a little bit more detail about what we can do with automatic machine learning. So in the data preprocessing section, we can do, this is just sort of a list of things that you do in data science. And of course, then we would want to automate all of these things. So with data preprocessing, that would mean things like imputation, different types of encoding for categoricals. You might do some feature selection or feature extraction. And then, well, I mentioned one-hot encoding, but there's all sorts of more sophisticated categorical encoding schemes. So target encoding is something that we've just added to H2O recently. And we are also adding it to AutoML. It's not in there yet, though. So that's one of the future things that we're adding is, let's say you have a column that represents zip code in your data. So does somebody know how many zip codes there are? Anyone? 42,000? I don't actually know. It's something like 40 or 50,000 zip codes. So if you have a column and you try to do one-hot encoding on that column, that's going to expand your data set by 40 or 50,000 columns, which is really just not a good situation to be in. Maybe some tools can support that, but typically that's not really a good way to encode categorical data. So there's a technique called target encoding, which is used very often by the Kaggle grandmasters as something to improve the performance. And this is one of the things that we rely heavily on in driverless AI to get really good automatic features. So we're going to do some basic stuff like that in AutoML in the future. Okay, so now let's say we've done our data preprocessing, and now if we want to generate models, there's a bunch of different ways we can do that. So the most straightforward thing would be to do a grid search or a random search. And then there's another type of technique called Bayesian hyperparameter optimization, which is a sequential approach to generating models where essentially each model becomes better and better as you go along, and there's a sort of like side model that's paying attention to which parameter values are getting good scores. So you train a model with certain values, and then you report what the, let's say AUC is, and then it will give you a new set of values to try, and then you report what the AUC is, and it's this back and forth thing, and so, that's how it works. So that's another way that we can generate models, but it has to be in sequence, so you can't parallelize that. And then different types of ensembles, like the main two that I'm familiar with are something called stacking or stacked ensembles or superlearning. It's all the same thing, different words, but same concept, and that's what we will do, or that's what we do in H2O and what I'll talk about. And then there's another type called ensemble selection, which is more of a greedy approach to ensembling. So I'm just going to show this same slide, and then this is what we have today in AutoML. So we have all the typical stuff that we have in H2O, imputation, one-hot encoding, standardization. We don't have target encoding yet, but we're adding it. So that's grayed out for now. And then the technique to build the models that we use is random grid search plus stacking. And why that works well is because stacking is a type of ensemble where if there's a lot of diversity in the set of models, that's when stacking does a good job. So one way to get diversity is to generate models randomly so that they're very different. And so if we combine these two things together, they fit very well, and we get a very good model at the end. So this is just an overview of what I've said already. So we do some basic pre-processing, which we already get for free because we're using H2O, and we already do that. So we train a random grid of GBMs, including H2O GBMs and XGBoost GBMs, deep neural networks, GLMs, et cetera. And we have chosen what the hyperparameter space is. So this is kind of us putting our expert data science knowledge into the tool. So we're choosing which hyperparameters to tune and then what the ranges that we should look at are. And so that's something that will also evolve over time as we have more sophisticated benchmarking tools for this so that we can tweak the ranges and maybe get better results. And we tune all the models individually using cross-validation. And then at the end, we train 2 stacked ensembles, one which will have all the models in it, and that's typically the best model when you sort them by performance. And then we have a lightweight model that we call the best of family. So what that is just, it takes the best model from each algorithm. So best GBM, best XGBoost, best deep learning, best random forest, best GLM, and it creates just a very small ensemble. So if you wanted to put one of these into production, I would probably recommend that ensemble instead of, let's say you have 100 models and you have a 100 model ensemble. Every time you make a prediction with a stacked ensemble, you have to make predictions from the base models, so that could take some time. So if you want something more production ready, we would recommend the best of family. And so what you get back from H2O AutoML is what we call the leaderboard. And the leaderboard just is a list, it's sort of a data frame, which lists all the models that you've trained and then the performance, and it's sorted by some performance metric. And you can specify how you want to sort. We have defaults, but you can change that. And just like all H2O models, they can be exported to production pretty easily. Okay, and this is what the flow interface looks like for AutoML. So this is just completely point and click machine learning. You click to upload a data set, you click to run AutoML, and all you have to do really is select which data frame you want to use, and then select which is the response column, and then you can tweak the other, the AutoML parameters if you want. But then you just press a button and a whole bunch of models will be trained. And this is what it looks like in R. So same concept, just import some data, one line of code, say how long you want it to run for. And this is, you've already seen this because we've seen the Python. And then, I don't know if you can read what's on this list from afar, but this is an example of a leaderboard. So I think this is if we ran AutoML on the Higgs data set, a 10,000 row subset. This is what we use in our user guide for the demo. So you could reproduce this leaderboard. And essentially what we see here, so this is a real result. We have stacked ensemble all models at the top with an AUC of 0.787, and then best of family right behind at 786. And then the top single model would be an XGBoost model, 782. And then it goes down the list, and you see different models that were trained. And so you might want to know what these models are. So these are just the model IDs. So if you want to look inside of any of these models, you just grab the model by ID, and then you can look at all the hyperparameters that were used and do some more exploration. And so some people might use this tool as just like a thing to run as the first thing in any data science project, maybe just see how it goes, and then based on what you see here, what you learn, then maybe revert to more of a manual process if you want to tweak, or you can run AutoML for longer if you want to get more models and see if it can do better. Or you could do sort of an iterative approach. Maybe then you do some feature engineering and see if that helps. Okay, I'm going to skip over this, I think, because I want to go back to the results. But I'll just say a couple things just so you don't get in trouble. So one thing just to notice is when you're running AutoML, it's going to create a lot of models. So you want to make sure that you have enough memory to store all those models, because the H2O cluster stores the data, it stores the models, it stores all the stuff that you're working with. So by default, it might just use a small amount of memory. So you might want to increase that if you find that you're running up against any memory constraints. And another thing that people might not notice right away is that the default runtime is 1 hour. So if let's say you want to say max models equals 50, And if you don't change the max runtime seconds, it'll still stop at an hour. So you might wonder, why did I not get 50 models? That's why. So if you want it to not be limited by time, you have to set that to some very, very high number, like 99999 or something. A lot of nines. Okay. And so here's just some links. So if you want to learn more, we have the documentation on AutoML is pretty extensive, and it will explain all the parameters and how to use them. And then there's code snippets in there. So I would say that's a good place if you just want a guide. And then we also have a few different tutorials. So different than the one that we just ran, a little bit more comprehensive. So they're in R and Python, and so that's a link to those. So I'll leave that up for a second. But of course, we'll always have these slides available afterwards, but just give you another second if you want to take a picture or something. Okay, so I'm out of time, so we're just going to go back to our AutoML here. And if you actually haven't run the leaderboard print statement yet, you'll see an old version. So you'll see probably GBMs as the top single models, and that's because when we last committed this file, it was run against an older version of H2O, and we've just added XGBoost. So if you ran it on, right now, and we refresh, we'll see XGBoost models in there. And we see the kind of typical scenario where the all models stacked ensemble is the best. Then we have the best of family, and then, not always is XGBoost gonna be the best, but on a lot of data sets it is, and it just depends on your type of data, like what kind of data you have. And so I know we have some extra time, more than we thought we would, so we do have more time, I think, to do some Q&A. So Michal's gonna come up now, and I guess if people have questions on Slido is where we're connecting. So I think okay. So we're just reading here. Okay, so the first question, does AutoML work with your stacker and ensemble code? So basically AutoML is a wrapper around that code, and so that's the answer to the question. So if you're already doing a lot of stacking or ensembling, you should just run AutoML. It's one line of code. You don't have to build up all the single models and then join them all together. Is H2O-AutoML free to use? Yes, it's part of H2O, so it's open source. Does it support wide data sets? Yes and no.
Working on it.
So that's, if you come to the AutoML talk tomorrow, you'll see that's one of the roadmap items, is adding better support for wide data sets via feature selection and feature extraction. Do you want to take any of those? What are the plans for AutoML in 2019? Top 3 things. Again, I'll talk about that tomorrow, but probably like the top things are automatic target encoding, blending. So there's something called, well, these words are not very well defined, but there's stacked ensemble, which uses cross-validation to do the ensembling, and then there's a variant of it called blending, where you don't use cross-validation, and because you don't use cross-validation, you can use it on time series data. So we have just added blending into H2O. It's not in a stable release yet, but it's in the nightly releases. So essentially, if you have kind of a time series data and you want to do stacking, you need blending, and so that will also go into AutoML. So that was 2 things, but we'll just anything.
It's being heavy on AutoML questions.
Yeah. Let's see. Oh, here's a good one. Difference between AutoML and driverless AI. So that's a big question. So there's a lot of differences. So from a data science perspective, one of the main differences is that driverless AI has automated feature engineering. And that is like a highly valuable thing that essentially requires manual labor. So you can either pay a data scientist to do that or do it through driverless. Some other differences are driverless is essentially built for GPUs. It can also be run on CPUs, but AutoML is built on H2O, which is primarily CPU, with the exception of XGBoost, which can be run on GPU. So yeah, CPU, GPU, so hardware differences and other things about productionizing models are different in H2O and driverless. I don't know if you have anything else to say about that.
We want to eventually converge driverless and H2O open source and make it a bit closer together. And as it was mentioned in the morning talks, we want to make sure that our users can use any size of data in driverless AI, and H2O open source seems like a natural fit together with sparkling water, so we can see that driverless will be using the H2O open source capabilities in the future. And also, we are thinking about how to use the driverless AI models in H2O. Maybe we can just take the output of the driverless as a recipe and retrain the model on the full data set. So we are definitely thinking about how to integrate those two products together and make them work together, because our typical open source user will probably use the driverless and vice versa. At some point, they will use both. I like the next question. Since H2O is open source, is there any way to contribute more models to the standard library? Yes, there is. I'm glad somebody asked. H2O is fully open source. You can find everything on our GitHub. And the code might be a little bit different than what you expect. It's machine learning framework. It's highly optimized. But we have our community channels. So if you want to contribute to H2O, don't hesitate to ask on Gitter, or we have a community Slack channel. And if you have good intentions, we will help you, and we will help you extend H2O. Or if you are not able to do it on your own, we will take over the work you did and finish it if it makes sense for our users.
I'll just answer one more question that I saw on there, brings us into our next talk. Can AutoML be used on Spark? And yes, it's part of sparkling water. And so, yeah, same thing. Basically, anything in H2O can also be used in sparkling water.
That's correct.
And so that will bring us to our next talk with Kuba, who's going to talk about sparkling water. So thank you.
Thank you.